In 2022, the James Webb Space Telescope pointed at the most distant galaxies we have ever seen. Galaxies so far away that their light left them when the universe, by the standard timeline, was only a few 100 million years old. What Webb found broke that timeline. These galaxies were not primitive. They had spiral arms, dust lanes, central bulges, structure that is supposed to take billions of years to build. According to the standard model of cosmology, these galaxies are simply too old to exist, too mature to have formed that fast. This is not a rounding error. It is one of a growing list of measurements that do not fit, and it is where our story begins. 20 years earlier, astronomers had already run into a version of this same problem. A star catalogued as HD 140283, nicknamed the Methuselah star, was measured at roughly 16 billion years old, older than the universe itself, which the standard model puts at 13.8 billion years. A star cannot be older than the universe that contains it. Repeated remeasurement narrowed the star's age, but even the most careful modern estimate, 14.46 billion years, still leaves almost no room to spare against a universe that is only 13.8 billion years old. Two independent methods, one star, one universe, and a contradiction that never fully went away. There's a second crack. When astronomers measure how fast the universe appears to be expanding today, using nearby supernova, they get one number. When they infer that same rate from the cosmic microwave background, the universe's oldest light, assuming the standard expansion history, they get a different number. The two disagree by about 9%. In precision cosmology, that is not noise. It's called the Hubble tension, and after a decade of steadily better data from multiple independent teams, it has only gotten sharper, not gone away. That crisis has only gotten sharper as our instruments improved, not softer. Every major leap in telescope resolution was expected, under the standard model, to eventually catch these distant galaxies looking young and unformed. After all, their light left when the universe was supposed to be a fraction of its current age. Instead, the opposite happened. Each generation of deeper imaging, right up through the James Webb Space Telescope, keeps finding the same thing. Massive, mature, fully evolved galaxies. Disks, bars, elliptical shapes, all the structure you would expect from an old galaxy, at redshifts of 6, 7, 10, 12, and beyond. In the recycling cosmos framework, that is exactly what you would expect. In an eternal, steady-state universe, there is no universal population of young structure waiting out at high redshift. Farther away just means a longer light travel time, not a less developed galaxy. This framework structure model reflects that directly. Its structure evolution parameter is set to 0 by default, no built-in aging with distance, and it is a free, measurable parameter, not an assumption. The standard model, by contrast, has to keep adding new early galaxy formation efficiency fixes every time a sharper telescope finds another galaxy that formed too fast. The cracks run deeper still. White dwarfs, the dense, dead cores of ordinary stars, cool more slowly than the standard model predicts, as if they carry more heat than they should for their age. The way galaxies cluster across the universe doesn't fully match the standard prediction either. And roughly 80% of all the gravitating mass in the universe is something called dark matter, a substance nobody has ever directly detected. Experiments buried deep underground to shield them from cosmic rays have searched for it for over 30 years and found nothing conclusive. Taken one at a time, each of these is a puzzle to patch with a new fix. Taken together, they start to look like symptoms of the same underlying mistake. Here is a different way to look at it. Imagine standing at the bottom of a swimming pool, looking up. Sunlight passes through the rippling surface above you and lands on the pool floor as a shifting, glowing pattern of bright and dark patches. If you didn't know about the water, you might think that pattern was telling you something about the sun itself, some structure in the light source. But it isn't. It's the water bending the light on its way down. Now scale that up to the size of the universe. The light we receive from across space has traveled through billions of light-years of matter and dark matter, bending and focusing the whole way. What if the patterns we see in that light, including the patterns in the universe's oldest radiation, are the pool floor and not the sun? The Recycling Cosmos Framework, the subject of this documentary, proposes something specific. Light continuously loses a tiny amount of energy as it travels by interacting with the Higgs field, the same quantum field that gives fundamental particles their mass. Not through collisions. There is nothing to collide with in empty space. Through a faint, continuous three-loop quantum process, the photon briefly becomes a virtual electron pair. One of those electrons emits a virtual Higgs boson, and that Higgs boson couples extremely weakly to the Planck scale. The coupling strength works out to about 3.12 times 10 to the minus 28, vanishingly small, undetectable in any laboratory, but acting on every photon, everywhere, for its entire journey. When light loses energy, its wavelength stretches. We call that redshift. Here is the critical difference from the standard picture. In the standard model, redshift is tied to the expansion of space itself, so a galaxy's redshift tells you when its light was emitted, and therefore how old the universe was at that moment. In the Recycling Cosmos Framework, there is no expansion. Redshift is simply a measure of distance, nothing more. A galaxy's light, being heavily redshifted, tells you it traveled a long way. It tells you nothing about how mature that galaxy already was when the light left it. That distinction resolves the James Webb problem we opened with. Picture two galaxies side by side, equally mature, equally structured, spiral arms, dust lanes, the same rich complexity. One is nearby, and its light reaches us bright and blue-white. The other is extremely distant, and its light reaches us dim and shifted deep into the red, simply because it traveled so much farther and lost so much more energy along the way. Neither galaxy is younger than the other. Distance is not a clock. The far one only looks strange if you assume, incorrectly, that its light is a snapshot of the young universe. It isn't. It's just far away. Look deep enough with James Webb, and there is no edge, no sudden absence of galaxies at greater distance. Just fainter and fainter light, shifted further into the red, all the way down. That is exactly what an infinite universe looks like from the inside. Population thinning only because of distance and the energy lost along the way, never because of a cosmological horizon, and never because of a moment when it all began. So where does that lost energy go? At a precise threshold, when a photon's energy drops to about 10 to the minus 5 electron volts, roughly the electron mass times the fine structure constant raised to the fifth power, light can no longer sustain itself as light. It undergoes a phase transition. It condenses into what we call dark matter. Not an exotic new particle waiting to be discovered, photons that have simply run out of energy and changed state, the way water vapor condenses into liquid. Using the mass ratio between this condensed dark matter and ordinary matter, drawn from galaxy rotation curves, clusters, and gravitational lensing, dark matter outweighs ordinary matter by a factor of about 5 to 1. Not the 68% dark energy, 27% dark matter split of the standard picture, but a direct, physical mass ratio with no dark energy required at all. No new particles. Just old light, in a different form. That sets up a cycle. Stars emit light. The light travels, losing energy the entire way. Once it crosses the threshold, it becomes dark matter, which accumulates gravitationally into vast halos around galaxies over immense timescales. Under the extreme temperature and pressure inside stellar cores, that dark matter can reconvert, turning back into hydrogen, fresh fuel for new stars, in brief, violent releases of energy. Light becomes dark matter. Dark matter becomes hydrogen. Hydrogen becomes stars. Stars become light again. The universe isn't expanding outward from a single beginning. It's recycling in steady state, and by the Recycling Cosmos Framework's accounting, it always has been. Here's where this becomes testable. In the standard model, the cosmic microwave background is a direct relic. Radiation released 400,000 years after the Big Bang, when the universe first became transparent. In the recycling cosmos framework, there was no such moment. The cosmic microwave background is ordinary starlight and galaxy light, redshifted by distance, until it lands in the microwave part of the spectrum. The accumulated, exhausted glow of an infinite universe, arriving from every direction. And exactly like the pool floor, the matter it passes through on the way here focuses and bends it into the bright and dark patches we measure as temperature variations. This model predicts the exact angular positions of all 5 major peaks in that pattern, from first principles, with 0 free parameters to adjust. The first peak, predicted 220.4, observed 220, 99.8%. The second, predicted 524, observed 537, 97.6%. The third, predicted 827, observed 810, 97.9%. The fourth and fifth land at 99.1 and 99.2%. 5 independent predictions. 5 matches, not fit to the data, derived before ever being compared to it. None of those 5 peak positions were chosen to fit the data. They come from a single physical scale. As light from a source galaxy travels to us, there is a coherent window over which it can still interfere with itself before losing too much energy, and that window sets a characteristic length, about 20.33 megaparsecs. Combined with how far, on average, that light has to travel through the universe's structure before reaching us, about 8,243 megaparsecs. That one number generates the entire ladder of peak positions, all 5 of them, from a single equation. Change the source coherence scale, and every peak position shifts together, in lockstep, exactly as we observe. It isn't 5 separate coincidences. It's one number, doing 5 jobs. The same framework predicts the actual temperature of that background radiation, using nothing but the electron mass, the fine structure constant, and Boltzmann's constant, no adjustable parameters at all. The calculation gives 2.68 Kelvin. The measured temperature, from the Planck satellite, is 2.725 Kelvin. Agreement, 98%. The recycling cosmos framework also predicts the rate cosmologists call the Hubble constant, derived here from the same underlying Higgs coupling, not fit to any expansion data. The prediction is 72.5 kilometers per second per megaparsec. Independent local measurements, using the distance ladder, give 73.3. That kind of agreement is not something you get by accident. It's what happens when the underlying physics is actually correct. For decades, the standard objection to any theory where light loses energy over distance has been simple. If photons were scattering off matter along the way, the images of distant galaxies should blur. They don't. The recycling cosmos framework answers that objection directly, because the energy loss isn't scattering off matter at all. It's a continuous interaction with the vacuum itself, the Higgs field, which is the same everywhere whether or not matter is nearby. That claim used to be an assumption. It no longer is. By comparing the cosmic microwave background temperature inside and around 726 of the largest known cosmic voids, the matter-coupled contribution to the energy loss can now be measured directly, and it comes out consistent with 0, bounded below 4.2 parts in 100,000 at 2 standard deviations. In other words, the light is losing energy to empty space itself, not to the matter it happens to pass near, to a precision that closes the oldest objection to this entire idea. That same 3-loop mechanism that converts light into dark matter and back into hydrogen also closes a loop through the densest environments in the universe. Inside a neutron star, the intense gravitational field and the surrounding condensed dark matter can combine, through a one-loop triangle process built from ordinary up and down quarks, to reconvert dark matter directly into protons and neutrons. The same reconversion this framework has already described, traced all the way down to the diagram. That triangle process makes a further prediction: a small family of new, extremely light particles tied to the energy scale of this interaction. One with a mass near 94.21 mega electron volts behaves like a graviton candidate, the particle that would carry the gravitational force. A second, near 133.24 mega-electron volts, is a light pseudoscalar particle, and a nuclear physics anomaly reported by the WA98 experiment at a very similar mass, may be the first experimental sighting of it. These are not free parameters, added to make the theory fit. They fall directly out of the same coupling constant that already predicts the cosmic microwave background peaks and its temperature. The list of matches continues. The way galaxies cluster across space, the cooling rates of white dwarfs, the abundance of deuterium left over from the earliest nuclear reactions, not from a hot Big Bang nucleosynthesis event, but from ordinary stellar and cosmic ray processes acting over unlimited time. In each case, this framework matches the data as well as, or better than, the standard model. And in each case, without adjusting a single free parameter to make it fit after the fact. Stack the cosmic microwave background around thousands of known galaxy clusters. Rescale each one by the recycling cosmos framework's predicted angular size, and a clear signal emerges. A faint hot ring, roughly 3 microkelvin above the background, sitting just outside each cluster's core, at 2.5 to 3 standard deviations of significance. That's consistent with exactly the kind of gravitational lensing residual the recycling cosmos framework predicts around concentrated mass. A small, real signature, sitting right where the physics says to look for it. To push the theory further, researchers built a computer model, a ray tracer, that takes the real mapped positions of galaxies, clusters, and cosmic structure, and calculates exactly how light would bend traveling through that structure under the recycling cosmos framework's physics. Feed it the universe as we've actually mapped it, using real catalogs of galaxy clusters and superclusters, and it tells you what the resulting, heavily redshifted background glow should look like by the time it reaches us. It isn't a picture. It's a prediction engine, and it can be pointed at any patch of sky and asked what should be there. In June 2026, that ray tracer was set loose on the real sky, searching blindly for anomalies, places where the recycling cosmos framework's physics predicts an unusual feature in the background glow. It returned a ranked list of candidates. The second strongest candidate on that list sat at galactic coordinates 209 degrees, minus 57 degrees. That is the exact location of the cold spot, one of the most studied anomalies in the whole cosmic microwave background, a feature that has puzzled astronomers for over 20 years. The ray tracer was never told to look for it. It rediscovered it blind, from physics alone, as its second-ranked prediction with a half-degree match. That same run produced 2 more strong candidates that don't yet have any known explanation. A cold spot at galactic coordinates 157 degrees, minus 30 degrees, and another at 216.7 degrees, minus 31 degrees. Neither has any catalogued void or supercluster nearby, but the void and supercluster catalogs barely cover that part of the sky at all. The recycling cosmos framework predicts both are sitting on real, unmapped concentrations of mass, dense enough to bend the background light we already have. That is a falsifiable claim, made before the observation. As deeper surveys map that part of the sky in the coming years, we will find out whether the mass is there, found after being predicted, rather than explained after being found. Not every piece of data agrees yet, and it's worth saying so plainly. The recycling cosmos framework predicts a flat effective Hubble parameter, HEFF, a fixed property of the Higgs vacuum, not an expansion rate, at every distance, but one dataset, a large catalog of galaxy ages measured as cosmic chronometers, appears to rise at greater distances, which looks like a problem for a flat prediction. Digging into it, that rise switches off exactly at the survey's completeness limit. Past a certain distance, the faintest, most metal-rich galaxies simply drop out of the sample, biasing the average toward the wrong answer. That's a real, promising lead, not yet a closed case. A theory that only shows you its successes isn't being honest with you. The recycling cosmos framework is still being tested against its hardest data, in the open, in real time. Step back And this isn't really a dispute over a few percentage points. It's a dispute about whether the universe had a beginning at all. The Standard Model says everything, space, time, matter, burst into existence 13.8 billion years ago in an event called the Big Bang. The Recycling Cosmos Framework says there was no such event. The universe is eternal, infinite, and in steady state, endlessly recycling its own light, energy, and matter, with no edge and no origin point. Those are not small differences in interpretation. They are two entirely different pictures of what reality fundamentally is. For a century, the Standard Model has shaped how an entire field thinks, teaches, and builds its instruments. Careers, telescopes, and textbooks have been built around it. None of that makes it correct. Science moves forward by testing ideas against data, and when a growing list of independent measurements stops matching the reigning model, that is exactly the moment to take the alternative seriously, not dismiss it because it's unfamiliar or because changing course would be inconvenient. This is not a finished case. It's an active one. Every prediction in the Recycling Cosmos Framework, the peak positions, the temperature, the Hubble constant, the vacuum coupling bound, the two unmapped mass candidates, was made in a form that future data can confirm or break. The next decade of deeper sky surveys, wider void catalogs, and next-generation gravitational lensing instruments will either tighten every one of these bounds towards zero or break one of them outright. That is what makes this science and not belief, the willingness to be proven wrong in public by the next measurement. The universe may be older than we assumed, larger than we assumed, far more patient than we assumed, recycling itself instead of racing toward an end, having never had a beginning to race away from. This is one theory's attempt to follow the data wherever it actually leads, even when that means setting aside the story we started with. The measurements are still coming in. So is the argument.